If you've been watching all the videos that I've posted to this unit of study, then you saw a linked YouTube video clip where a bungee jumper holding a cookie falls through the air, approaches a glass of milk, and in the close-up view you can see that everything was set up just right, so he just dunks the cookie into the milk. So we're going to try our own version of this with our Albert Einstein action figure, and we'll have him jump from this platform. Notice that the string is in its very relaxed position here, and Einstein will fly through the air, and if we get everything set just right, we'll determine the correct distance so that he just barely splashes his head into the water without actually hitting the ground. Okay, so we're going to model this as a somewhat simplified diagram. So the sphere you see here represents our Albert Einstein. And I'm going to label 4 different positions. So position A is obviously the starting point, the initial. And then in position B, here's what's special about this one. That's when the string has 0 tension in it. So we say this is the string at its natural relaxed length. Okay, then in case C, there's some stretch, as you can see highlighted in pink here. We'll call that X. So if we were to add L naught with X, we would have a new greater length of the string that we call L. Now, what's special about this point C? The amount of stretch X at this point, right, here's where there's no tension at all. This would be the point where if we were to just take our hand and hold our Einstein action figure and then gradually bring him to a state of equilibrium, that would be the point at which his weight is offset by a certain amount of tension. In fact, we're going to assume that this elastic cord behaves according to Hooke's law. So this tension, we'll label it in this diagram, would really just be equal to Kx, where the x you see in this expression is this particular value of x highlighted here in pink. So if we can measure this value of x, we could use that to determine what the spring stiffness is. Okay, and then, of course, Einstein continues to descend toward the water, and if we get everything set up just right at this point, he's back at rest again for an instant in time, right? His instantaneous velocity will be equal to 0. So the stretch we already identified as x, and then beyond that, there's an additional amount of stretch that we could label as d. And of course, a free body diagram in this case, there'd be no change in the vector mg, but the upward tension would now be k times the quantity x plus d. In other words, that tension would be greater than his weight. Now, what does that mean? That means there's going to be an upward acceleration. That doesn't mean he's moving upward at this instant. In fact, his velocity is 0, but he's accelerating upward, which is why he would turn around from this point and then start to bounce back up. Okay, so let's label all this again a little more clearly. So these are our key variables. You see m for mass, of course, and then we've got all these various lengths. The initial length, when there's no tension whatsoever in the cord, and then its stretched length when it goes an extra distance of x. And then we're going to label the whole distance from the starting point to the ground as some total value h. All we need to do is apply the law of conservation of energy. And it's true that the energy at point A equals the energy at point B equals the energy at point C equals the energy at point D, but we can cut out the middleman, so to speak. We don't need to know the energy at points B and C. It's totally valid to set all the mechanical energy at point A equal to all the mechanical energy at point D. Okay, so at point A, that represents Albert Einstein at rest because the cord is relaxed. There's no elastic potential energy. In fact, all there is gravitational potential energy. So we'll set the reference level height equals 0 at the ground. And this means at point A, the potential energy is mgh. When he gets to point D, remember, that's momentarily at rest, and he's at the reference level at point D, so there's no kinetic energy. There's no elastic potential energy. In fact, the only energy, there's no gravitational potential energy. Let me restate that. There's 0 kinetic energy. There's 0 gravitational potential energy. There certainly is elastic potential energy because the spring has been stretched x plus d. Okay, so we'll call this 1/2 k times the quantity x plus d squared. So there's step 1, and all we really need to do is work through this equation so that we can solve for d, and that'll help us set up this apparatus. After all, when I set this up, I can control this screw right here where I can raise or lower the Einstein so that this distance d is the exact safe distance to allow him to just barely splash into the water. So we're going to make some substitutions. What can we substitute in place of h? Well, h appears to be the length L that we have labeled here in the diagram plus the length d. Simple enough. So this becomes mg times the quantity L plus d, and that equals 1/2, let's see, what can we substitute for k? Well, based on this special point C, recall what's special about this point. If we are to measure this value of x, then we know at point C, that's the moment of equilibrium. mg equals kx. That means k is equal to mg divided by x. Yeah, that's what we'll substitute. Okay, now what can we cancel out? This is kind of interesting. M and G show up. So when we do this demonstration, it's not actually important to measure the mass of the Einstein action figure. Okay. So in the next step, I'll multiply the equation through by 2x. We have 2x times the quantity L plus D is equal to, well, and then I'll also expand the polynomial. So we'll get x squared plus 2xd plus d squared. I'll also distribute on the left, so we have 2xl plus 2xd is equal to x squared plus 2xd plus d squared. So this term 2xd cancels out on both sides. So this leads us to step 5. We'll rearrange to solve for d squared. It looks like d squared is equal to 2xl minus x squared. So finally, d would be equal to the square root of 2xl minus x squared. In the next video, I'll show you the measurements, but I'll give them to you now. I've set it up, and I found that the value of x, which, let me remind you, is really the difference between L naught and L, right? That's this value x right here. So x equals L minus L naught. And when I measured it, that was equal to 113 centimeters minus 99 centimeters. So x is 0.14 meter. Okay, and then I measured the value of Oh, well, I didn't have to measure anything else. I've got my value of L. That was 1.13 meter. And then I've got the value of X, 0.14. And that same value is 0.14 squared here. So when I plugged it into this formula and worked it all out, what did I get for D? I'll give you a moment to reach for your calculator and plug in and see what you get. Double check my work. Okay, did you get the same thing as me? Right, I got 54.5 centimeters, or 0.545 meters. Well, I have to be careful. If I were to grab him with my hand, lower him down until he reaches this point of equilibrium, and then set the distance above the floor as that value, we'd have problems, right? I don't want his head to hit the floor. I want it to hit the top of the water. So I measured the height of the water in this beaker, and that was about 9 centimeters. So I actually had to set him a distance of 63.5 centimeters above the floor. Right, that's 9 centimeters. And then from the equilibrium point down to the ground is 54.5 centimeters. So I actually had to lift everything up this extra 9 centimeters. So you'll see in the next video all the measurements, and then I'll also record one more time, and you'll see that he just barely splashes into the water. Okay, so there it is. Just one more example of applying the law of conservation of energy. Hope you appreciate it. Thanks for watching.